really enjoyed the last lecture of the workshop, the school. So first what I'm going to do is the talk is divided into two parts, as all of the other talks. I'm going to talk about modern SAT solving, some of the basic ideas behind modern SAT solving, and then in the second part we're going to apply modern SAT solving to solve optimization problem, which is called Maxsat. So modern SAT solvers are called CDCL solvers, conflict-directed clause learning solvers. So why do you want to do SAT solving at all? Well, the idea is that you have lots of practical problems that are in the class NP. They're hard, and there's no way around it, but they're problems that you need to solve. So, well, you could build a special purpose algorithm that tries to solve the instances that you need to solve. Of course, it's always going to be foiled by some inputs, but maybe for the inputs that you have in your application, most of the time it works. The other alternative is what you can do is, since you know that SAT is complete for the class NP, you can always encode your problem into SAT. And then you can take an off-the-shelf SAT solver that's been highly engineered and well-engineered, and you can use that to generate a solution to your SAT problem, and through your encoding, you can then translate it back to a solution to your problem. Okay? And so you get a solution to your problem without having to build a special purpose algorithm for solving it. You just use an off-the-shelf SAT solver. And the question, of course, is can this approach be successful? And yes, it can. In fact, for many problems in verification in other areas, SAT solvers have sort of taken over because they're more efficient than other ways of doing things. So they have been used a lot, and in many cases when people think that they can't solve a problem exactly, they can in fact solve these problems with SAT solvers. And this approach generalizes. So there are many other complexity classes besides NP, and most of those complexity classes have their own version of a complete problem. Usually it's a logical problem. We'll talk about Maxsat later on, which is complete for the class FP to the NP, which is a class of problems that can be solved in polynomial time with access to an NP oracle, function problems. And there are other problems like SharpSat, which is complete for SharpP and other things like that. And you can build, in a similar way, general problem solvers for these logical versions, and then convert your problem to that and use the solver. So I'm just going to assume that to go through some very basic stuff that you may or may not have seen. You've probably seen them. And SAT solvers work with conjunctive normal form formulas, which are literals, propositional variables, or their negation. That's a literal. And then a disjunction of literals is a clause. And then a conjunction of clauses is a CNF formula. Often we will write it without the disjunctions in the middle. We just write them as a list of literals in a clause. And you know about truth assignments too, I'm sure. You can assign true or false to a propositional variable, and the negation of that propositional variable gets the opposite truth value. And a clause is satisfied if at least one of its literals is satisfied, in other words, has the truth value 1. And the formula is satisfied if every clause has the truth value 1. So you say that a CNF is satisfiable if there exists a truth assignment, in other words, an assignment of true-false to the propositional variables that satisfies all of the clauses. And you also, what's useful as well is the idea of logical consequence. You have another clause F. You say that F is a logical consequence of your input formula, big F, if every model of F, every truth assignment that satisfies F, also satisfies little f. So that's the notion of logical consequence, and we often write it with this double turnstile notation, which is the semantics. And also there's some obvious simplifications you can do with clauses. So for example, if a clause has both a literal and its negation, then it's clearly true under every truth assignment. Either the negation is true or the original is true, and that's a tautology. You can get rid of such clauses. And sometimes during reasoning, you might generate some tautological resolvents, they're called. And so you can get rid of those. If you have duplicate literals in a clause, you can get rid of those. And you can also use this somewhat more difficult to detect, but you can do it in different ways. notion of subsumption is if you have a clause that's a subset of another one, you can get rid of the superset, right? So it's subsumed away. And people use various techniques involving Bloom filters, for example, to quickly detect possible subsumptions. To give an idea, sort of intuitive idea about CNF representation, it's useful to think about a clause as basically blocking certain types of truth assignments. And therefore, the empty clause, by convention, is considered to block all truth assignments. It's unsatisfiable. Satisfiability, of course, we know is NP complete. So to get an idea about this, so say we have this truth value over ABC, so true or false under different assignments. And we can see that every clause, like the clause A, will block some assignments. All the clauses where A is false, if there's a unit clause A, you're going to block those. If you have a clause not A or C, you'll block another pair of truth assignments. And so you can see that if you have a bunch of clauses, you're blocking these intersecting sets of truth assignments. It's a combinatorial problem to determine whether or not there are any truth assignments left. Right? That's where the combinatorics comes from. Okay, now you can convert any formula, any propositional formula, into CNF by the introduction of new variables. If you introduce these new variables, it's an idea due to cite in, then you can do this with a polynomial increase in the size of the formula. If you don't introduce new variables, you could potentially have an exponential increase in the formula, so people always introduce these new variables. And CNF itself is not really that natural a language. It takes a little bit of working with CNF to get an idea of what a CNF formula is saying. But in different domains, you might have your own kind of language. Like if you're talking about automated planning, which is an area of AI, you would have a specification of actions in what is called strips. Or if you're dealing with hardware, you might talk about circuits. Or if you're doing it in software, you might talk about verification in some language. You have some statement in some verification language. And now these is the language you use. But often what you do then is you can translate that language or assertions in that language, as we saw earlier on when Tom talked about some of their translators. You can translate those languages into CNF. And that's typically what you do. People usually don't write CNF raw. They often write some other more complicated language and then translate to CNF. And the way that you do the translation actually has a big impact on performance. So some translations, some encodings are efficient for SAT solvers, others are not so efficient. So the key thing about CNF is that it's very simple, and that means the software, the SAT solver, can do very simple things. And that's key to get it to be efficient. And there's only one thing you really can do with CNF when it comes to reasoning, and that's resolution. So you have a clause with A and X in it, and another clause with B and not X, where A and B are sets of literals. So in other words, these two clauses clash on the literal X. You can get rid of the clashing literal and generate the new clause, which is A and B, A union B, right? And normally we assume that A union B don't have another pair of clashing literals, because if they do, then you would get a tautology. Okay? So we know that resolution produces logical consequences. In other words, any truth assignment that satisfies C and C prime will always satisfy the resolvent in C and C prime. So it's a sound rule of inference. And now you can chain steps of resolution together to get a derivation or a proof. You can take a sequence of clauses C1 to Cn, and the property is that each CI is either an input clause or is a result of having resolved together two prior clauses in this sequence. And then such a thing would prove this last clause. So we have a sound sequence of inferences that generates Cn. And then that means you can write it, because you have this sequencing constraint that every resolvent has to depend on two prior clauses, you can rewrite every resolution proof as DAG. So if we look at this example here, we can resolve to produce this clause A, B, E, or F. And that's the sequence of resolvents, and that is the resultant DAG, right? So the DAG form is important because certain DAGs have certain structural features. So usually what we're interested in is producing resolution refutations, and that's just a resolution proof that generates the empty clause. And because resolution is sound, you know that if you have an input formula, and from that formula F you can produce the empty clause, then any truth assignment that satisfies F must satisfy the empty clause. And of course there's no such thing, so therefore no truth assignment satisfies the original input F. Okay? And resolution is refutation complete. It's not complete in the standard way. In other words, there are clauses that follows from F that you cannot produce by resolution. However, if you take the negation of that clause and you add it to F, you will also always produce a refutation. In other words, for any logical consequence, if F implies little f, by logical consequence, if you negate little f, add it to F, you can produce a contradiction. So it's complete in that way. So CNF and propositional reasons have been around for a long time. And in 1962, this backtracking algorithm was generated by Davis, Lodgman, and Loveland, called DLL. But nowadays it's called DPLL because of prior work by Davis and Putnam. It's a backtracking version, a backtracking algorithm that solves satisfiability. It's not a particularly good algorithm, and I'll explain why. But it has served as the basis for modern CDCL algorithms. So let's take a look at how it operates. Basically, you can think about it recursively. It's really exploring a tree. And you take this input formula and you have a set of literals that you've made true so far. Initially, that is an empty set of literals, and F is your input formula. So you check to see, is F empty? Have you satisfied all the clauses? Then you know that pi is a truth assignment that satisfies F. You can return satisfiable. If F, on the other hand, contains an empty clause, you can't satisfy F, so now you can backtrack. So you just return unsat. Otherwise, what you have to do is you don't have one of these situations where you know the answer yet. So now you pick a variable, v, and you try to assign v to value true. You reduce the formula by that assignment, and you recursively call yourself with the assignment augmented by v. If that result is sat, you don't need to go any further. But if it's unsat, you need to try the other side. So now you have to try to reduce f by not v, and then do the recursion there. Okay? And what is this reduction? Well, the reduction is pretty simple. It's that if you have a formula of CNF and you assign the literal v, a literal L, what you're going to do is you're going to remove all the clauses that have L in it because they're satisfied by L. And you're going to take all the clauses that have not L, and you're going to get rid of the not L because those clauses can no longer be satisfied by not L because not L is false. Okay, so if you reduce this example here by D, what will happen is that this clause will vanish, and this one will get its not D reduced. Okay, so if we do an example of run in DPLL on this simple formula, what we see is that, first of all, we can branch on any way we wish. So over here, under not X, I've decided to branch on Y, where over here with X, I've decided to branch on R. And that actually is quite important for the efficiency. If you always branched on the same variable at every level, you would generate what's called an ordered resolution, and that's known to be less powerful. Okay, so here you can branch on anyone, and notice that once I branch, what's going to happen in this case is that some of these things end up with false or empty clauses, and I've put those in red. So these are input clauses that are falsified at that point in the search. So for example, here, X and Y is falsified because we've made not X true and we made not Y true. Over here, we have not R, not Z. That's also an input clause. And it's been falsified because we've made Z and R true. Okay? Now you go along the whole way. If the formula is unsatisfiable, every one of these leaf nodes will have a clause that has become false. Now why is that useful, important? Well, if we take a look at what we can do with those clauses, we can actually resolve them together. So we can label the internal nodes. So remember that this is an internal node here, and these are the two leaf nodes. We can label this internal node by the resolvent of the two leaf nodes. And you can see that these two clauses resolve together with the z and the not z, and you get x or not r. And you can do that all the way up the tree, and what will happen is you will get the empty clause at the top. And that's always going to be the case. And so we see that what's happening here is that a run of DPLL is producing implicitly a resolution proof. It doesn't actually keep track of these clauses, but it just detects the leaves have falsified a clause. But from that run, from that tree, you can produce this tree resolution. Now this resolution, if you're looking about it as a DAG, has this special form. Like I said, it's a tree. Okay? And so that's bad news, because tree resolution is a special form of resolution. It also is sound. It's complete. In other words, every unsatisfiable formula has a tree resolution as well as a general resolution. Okay, so it's refutation complete. But unfortunately, it can be big, much bigger than a general resolution. And what's happening with tree resolutions? Well, with tree resolutions, what's happening is that you cannot reuse a formula that you've derived. You cannot reuse a clause. If you want to take this resolution proof that uses C as an input to both of these two clauses, you're going to have to basically change this into a tree where you have a new copy of C and you have a new copy of everything that you used to derive that clause. So tree resolutions have no memory. If you're going to use a clause more than once, you have to derive it all over again. Okay? And as a result, DPLL can often be very inefficient. Now, there's actually a precise way of understanding that, and that's some work that was done quite a long time on proof systems by Cook and Rakau. And they defined this proof theoretic notion of a proof system as simply an algorithm. It's a polytime algorithm, and it has it over a language L. And it basically says, okay, I have a formula in L. I have a string that's in L. And I have another string, which is the proof. And this polytime algorithm can run in time polynomial in the input form L, string L, the input string F, and the proof P. If it says yes, then you know that this string F is a member of this language L. So for example, if we take L to be the set of all strings that are unsatisfiable CNFs, then we can take our proofs to be resolution proofs, sequences of clauses, and in time polynomial in the resolution sequence and the input formula, we can determine whether or not that resolution proof really is a proof of unsatisfiability for F. Okay? So it's a sort of a general way of thinking about proof systems, just as these strings. And then you can measure the, Yes, that's why it works. That's why when you have this resolution proof, checking that every step is correct does in fact give you a verification that F is unsatisfiable. Yeah, it generalizes because now your language can be arbitrary things. It's not just CNF. It could be propositional formulas expressed as circuits. And your proof, your string that's your proof, again, could be complicated things. You could do some arbitrary polynomial computation at every step. So it's very general in that way. Okay? And now the complexity then, once you have this definition, you can say what the complexity of a proof system is. And that is you take a look at all strings in your language that have a fixed length n. and you ask, okay, of these, I want to find for each one of these the minimum length proof. And now I look at these strings and I say, what string has the maximum minimal length proof? Right? So this string has a really long proof, has no shorter proof. And that is going to be the complexity of my system. So in other words, a worst case complexity, right? It's saying that there are formulas of length n that have some very large proof. And the minimum size proof is very large. And we know that resolution has exponential complexity. There are formulas of length n that have 2 to the n length or exponential length proofs as their shortest proofs. Okay? So it's a measure of how fast this proof size can grow in the worst case. And then with that notion, we can define this notion of p-simulation, which is that we have 2 proof systems, PC1 and PC2, and we say that PC2 can p-simulate PC1 if there's a function that converts proofs in PC2 into proofs of PC1 in polynomial time. In other words, any proof in proof system number 2 can be converted to a proof in proof system number 1 that's not much bigger. It's polynomially sized. And so what we know from all of that is we know that trace resolution cannot p-simulate general resolution. In other words, there are proofs in general resolution that cannot be converted to tree resolution proofs without an exponential blowup. Okay? And that means that since DPLL's search algorithm is generated in tree resolution, there are some formulas for which small proofs exist in general resolution, but any run, no matter what you do, no matter how you branch on the variables, any run of DPLL will be exponential, right? Because every one of those generates a proof, and we know the minimum size proof is exponential. So that is sort of, if you, in fact, in practice, although this is a theoretical notion, if you run DPLL, you realize that it's really a poor algorithm for solving SAT. However, it does give you some ideas about how you can extend this. And we saw that the main idea that for tree resolution is that tree resolutions have no memory. So we can try to fix that. And that's what CDCL does. A main part of CDCL is that it does clause learning. It remembers some of these clauses that were generated so it can use them in other parts of the search tree. Okay? So it does a few things. It's, first of all, it's based on, yeah? It says nothing about space. That's right. So it could be that you need exponential space, and sometimes you do, but okay. But then you'll need exponential time because you have to generate all those clauses anyway. So time kind of covers space in this sense, right? So these modern SAT solvers, they're based on backtracking search, DPLL. They have more efficient implementation methods, and they do clause learning, which gets around this tree resolution limitation. And that's done by explicitly keeping track of the clauses that get falsified at the root and keeping track of other clauses, basically, so you can do the resolution steps. And then it also uses these learned clauses to heuristically guide the search, which variables to branch on next. And that's the conflict-directed part. So clause learning and conflict-directed. Okay, and there's other advances that people have made as well that are quite significant. So let's take a look again at this DPLL algorithm. And we see that what do we need this formula f? So remember what we're doing is we're restricting f by the decided literal, and we are recursively calling it on that new f. So what do you need from that f? Well, you have to be able to detect if there are empty clauses. And you have to detect if there are any unit clauses, because one important component of DPLL is that it prefers to branch on variables that appear in unit clauses. And that turns out to be very important to do. Okay, so you need these two things. So you need to be able to find empty clauses and unit clauses. So how do you detect units efficiently when you have 10 million clauses? Right? And you have to do that at every time you make a decision. So you're doing a search that has 1 million decisions, and you have a formula that has 10 million clauses, right? So how do you do this? Well, you obviously can't compute the reduction because that's a lot of work. And the worst about that is if you compute the reduction, when you backtrack, you have to uncompute it. You have to undo it, right? That's a lot of work. So how do you find units? Well, what we're going to do is we're not going to compute this reduction at all. We're just going to value the literals. And we're going to take a look at the input literals, input clauses, and we say, okay, does that clause have a true literal in it? It's kind of removed. Does that clause have completely false literals? It's empty. Does that clause have all but one literal false? It's a unit clause. Okay, so that's the first thing. So we never touch the clauses. We just value the literals. And now we want to detect these things. And one other important thing is that if you detect that the clause is unit, so you detect that x is forced, you're going to set x to be true because you have to set x to true. Now, that could mean that some other clause becomes unit. So here, because you set x to true, this clause now becomes unit and it forces R. So this sequence of setting clauses that are literals that are in units and then generating more units and set in is called unit propagation. And you have to do this. And in a modern SAT solver working on most formulas, you can get chains that are hundreds and thousands long of unit propagations. So you have to do this efficiently. So here's what kind of like it's going to look like. You have, at the root, you have not made any decisions, but the input could have some units in it, especially after simplification. So you're going to set those units, and then it may force some other units. So you're going to do a whole chain of unit propagation. And then you get to a point where you can't force anything else by unit propagation. Now you have to make a decision. And then after you make that decision, which is a variable that has not yet been set, again, you're going to get unit propagation, and you're going to get a bunch of units. And you're going to keep on doing this. Okay? So basically what we want to do is down this trail, we want to, at this point, after we've set t, we want to detect units. Okay? So, well, how could you do this? There's an old way of doing this. And basically what you do is for every literal, you keep a list of the clauses that it appears in. And you keep a count of in every clause of how many false literals are in that clause. And so when you set x to false, you increment the count of the variables, the clauses it's in. And if any of those clauses have length, k, if there's k minus 1 false literals in them, then you know that clause has become unit, right? So that's a relatively simple way to do things. But you have to visit every clause that x appears in. And worse, you have to undo those counts when you backtrack. So when you unset x, you've got to undo all those counts. So that's painful. So instead, the technique that was part of why SAT solvers became so efficient was this watched literal idea. And what you do in that case is you simply select 2 literals from every clause, and those are the watch literals for that clause. So every literal now has a list of clauses that it watches, which is a subset of the clauses it appears in. And now when a literal becomes false, all you need to do is check the clauses it watches. Okay? And so you know that if the clause is going to become unit, at least one of its watches must be falsified. That's the idea. So you can wait until one of the watches is falsified. You don't care about the other literals in it being falsified. And that means once it's false, you just examine that clause to see if you can find a new watch, or if the other watch is true. If you can't find a new watch, then the clause has either become unit or has become empty. Okay? And so if it's become unit, or it's not, if you can find another watch, what you do is you move that clause from X's watch list to this new watch. Okay? And you keep on going. And the nice thing about this is that you only need to check a fraction of the clauses that X appears in, the ones that it watches. And most important is you don't need to do anything at all in backtrack. because if the watches are valid, when you go backtrack, the watches remain valid. Okay, so that's a critical element. So backtrack becomes cheap. And as we'll see, backtracking is used a lot. So that's how you manage to detect units. Now, what about causal learning? When you find an empty clause, you find a clause that's falsified, you will backtrack. You've hit a dead end. And CDCL also backtracks, but it does it in a slightly different way. What it's going to do, it's going to backtrack, but it's going to learn a new clause, which will block that particular path from occurring again, and other paths that are similar to it. That's the key notion. So let's take a look. So we have a trail. The literals with red dots are the decisions we've made. The literals with blue squares are the unit implied literals. So we have a trail with decisions, and intermixed are some unit implied literals. Now we've got to this point where this clause is being falsified. Okay? So all you can see for every one of these, one of its negation has been set. Okay? So now what we can do is we know that what we're doing is when we do unit propagation, we keep track of the reason why every literal is unit propagated. So each of these unit forced literals has a clause associated with it as being the reason why that clause became unit. So if, for example, we take a look at this clause here, these are all being falsified, and this clause became unit, forcing that. Okay? So what we see then is that the clauses that are falsified in each of these units appear above K in the trail. In other words, they were falsified before you implied K. And that means that you always go upwards. And that's an important constraint. Okay? And what we can do then is we can take this conflict clause, and that means that we can resolve that conflict clause. If we have any forced literals in that conflict clause, we could resolve that literal against the clause that forced that literal. So for example, we have a not D here. Okay? That means that, of course, that D appeared somewhere on the trail, because this conflict clause has literals that were falsified on the trail. And that D has itself a reason clause, which positive version of D. So we can take that and resolve it against that. And you're always going to get now a new clause that's falsified by the trail. And you can do that for any of these forced literals. In this example here, we know that K was forced. Not K was forced. This is the reason for not K, and therefore we could resolve that K against that, and we get a new clause. So we can do this for any of these. Okay? Now, you could keep on doing this. You could do this iteratively until the resultant clause has only decision literals in it. In other words, if you kept on doing this, if you take this D and you resolve it away, you get this clause here. And then if you resolve the B away, you get this clause here. And you can keep on going, resolving all of these forced literals away by their reasons, and you're only going to end up with decisions. Okay? And that tells you that that sequence of decisions was no good, right? And that's called the all decision clause. But usually you don't want to do that. The reason why you don't want to do that is the resultant clause, this all decision clause, is too specific to this particular path. You want a clause that blocks other things, not just this reason. Okay, so empirically, the all decision clause turns out to be not so great. The one that is used is called the one UIP clause. And the one UIP clause basically continually resolves away the forced literal that's deepest on the trail until you only have one literal left at the deepest level. And then now you have a clause which has one literal at the deepest level, and all the other literals appear higher up, and you can use it to backtrack. So how does this work? So say, for example, we get to this conflict clause here. We can see this conflict clause The literals in blue are all the literals that appear after the Z decision. So they're the deepest level. Okay? So I'm going to proceed to resolve away these in order of this trail, going backwards. So the deepest one is not K. So I resolve that with its reason for not K. I get this clause. Then I take the I, and I resolve it with the reason for I, and I get this clause, not H, and all that stuff. And this clause, you can see, only has one literal at this deepest level. All these other literals, the not F appears at this level, the E appears up here, the D appears there, the B appears up here, so they all appear higher up before the Z decision. And what we see about this clause is that this clause is actually implying that not H was true as soon as we made F true. So as soon as we made F true, this clause became unit and implied not H. But we didn't know that because we didn't have this clause, right? So what we're going to do then is we are going to backtrack to the point where that clause became unit and force that literal. Okay? So that's why these 1UIP clauses are called empowering clauses. They're called unit empowering clauses because basically what they do is they increase or improve the power of unit propagation. So every time you add one of these clauses, unit propagation can now conclude something that it couldn't conclude before. Okay? So what you do then is, like I said, you take this deepest literal and you look at the second deepest literal in the clause and you backtrack to that level and then you force that clause by unit propagation and you continue on. So that's what's going to happen here is we have this clause here. We generated this unit 1UIP clause. It's forced after F. So we backtrack across this Z decision and then we force it and then we continue onwards. Okay? And that's how a SAT solver works with its learned clauses. And after, of course, after you've done that, you're going to be able to get potentially more unit propagations. And then after you finish unit propagation, you make another decision. It might be Z, it might be something different. So we see a couple things. First of all, we are actually backtracking across incompletely explored decisions. When we backtrack across Z, we know Z is not going to work. Z leads to a contradiction. But it could be that not Z had a solution under it. Instead, we're backtracking and doing Z altogether. Okay? So it doesn't explore the space in the systematic way that DPLL does. DPL leaves no possibilities unturned, right? So it's still complete, but you have to argue that completeness from a different point of view. And the completeness basically comes from the fact that you're learning clauses. So if you keep on learning clauses, there's only a finite number of clauses you can learn. Yeah? Pardon? No, we're no longer doing tree resolution because what we're going to do is we're going to remember this clause in our database and keep it for future pass.
So I can mix it with anything else.
That's right. Here, it happens to be unit, but when we backtrack further, we can use it again on another path. Okay? So we have a couple things that are going on. It's cheap to backtrack because of our 2-watch literal scheme. Going back far enough so we can fix the trail makes the implementation more efficient. And it allows basically the search to explore a different area. So it gives the search a little bit more freedom. It doesn't have to keep on going down here. It can backtrack and try something else. Okay? And in fact, unit propagation often finds unit clauses. So when you solve a problem of these large industrial problems, you'll often get thousands of unit clauses that you learn. And every time you learn a unit clause, you're going to backtrack basically to the root before any decisions are made. And so these learned unit clauses actually generate restarts of the solver. Okay? So, so that's clause learning. Now, another big component of SAT solvers is what's called the VSIDS heuristic, or variance of the VSIDS heuristic. And that stands for variable state independent decay in sum. And I'm not exactly sure why the state is independent, but anyway, that's what it's called. That's not so completely understood. People have rough ideas about what it's doing, and it works very well in practice. But there's no theoretically good, sound explanation of what this heuristic is doing. But basically what the heuristic does is that every time you do a resolution of a clause against something, the reason for a unit, when you do clause learning, like for example, in this case here, when we learned this, we did a resolution against this clause, then we did a resolution against this clause to get this clause. Each of these clauses, including the conflict clause that we originally got, the very first one, what we do is we bump their variables by 1. We increase their variables by 1. And then what we do is we periodically divide all the counts by 2. And that means that the old counts get exponentially decayed. And the variables that appear in recent clauses get a higher relative value. And what we do is we pick an unassigned variable that has the highest count. Right? So that's what's called VSIDS. And you can do that with a heap. So you don't have to sort the clause at the variables, and you can update the heap, and it's fairly efficient to do that. And basically what's that doing is that it's causing the SAT solver to branch on the variables that appeared in recently learned clauses. Why does that work theoretically? We don't really understand. But it does seem to work empirically. Another thing that's used in SAT solvers is what's called phase saving. And that is, you go down a trail, you set the variables in a particular way. Now you learn a unit clause, or you restart, you jump back to the root. What you're going to do when you go down the next trail is you're going to prefer to use the old assignment. It's called phase saving. And so it's sort of like what happens in this case is that you're kind of going back to a similar part of the search space, because you're setting most of the decision variables to be the same thing. And then occasionally you will also restart the system and jump back to the root. So it's a very funny behavior, because normally in the original descriptions of restarts, people said, okay, what restarts help you do is to go to a completely different part of the search space. But with phase saving, actually you're kind of coming back to the same place, but it's still effective. So our explanations about why restarts work don't really hold anymore. But so that's an interesting thing to understand future. And now you can prove as well that you go beyond true resolution with these clause learning. In fact, you can show fairly easily, maybe too easily, that if you do restarts, you can p-simulate general resolution. Now, the problem with that is that the way that you prove this is you basically run the SAT solver and restart after every clause you learn. And then it becomes trivial to see that you can p-simulate general resolution. It's much more difficult, and I've done some work on this. It remains unresolved whether or not CDCL without restarts is as powerful as general resolution. We do know it's easy to show that it's at least as powerful as regular resolution, which is a generalization of tree and ordered resolution. So it definitely is more powerful than true resolution. But we don't know, if you don't use restarts, whether or not you're as powerful as general resolution or not. And then to finish up, there's a bunch of other techniques that are used. You get this clause, this one UIP clause. Sometimes you can search for other sequences of resolution steps that reduce this clause in size. It's called clause reduction, and that's a powerful technique. When you learn more and more clauses, the solver starts to slow down. Every time you learn a clause, you have to have 2 literals that watch it. So the watch lists grow. So every time you value a literal, you have to explore a bigger watch list. And over time, the solver becomes very slow. So it becomes very important to forget a bunch of clauses. And the latest technology in this is what's called LBD. LBD, what that number is associated with every learned clause. You compute how many literals, with every literal there's a decision level, and you count how many different decision levels appeared in that clause. And that's the LBD. And then after, in some of these SAT solvers, after 10,000 learned clauses, you basically sort the clauses by their LBD, and you get rid of the half that has highest LBD. Except perhaps you keep the clauses that have LBD 2. Okay? And that's very effective as well. With this, you lose the guarantee of completeness unless you increment this number 10,000 slowly over time. But I mean, you know, completeness is okay, but you can't wait forever either. So that's, in practice, completeness doesn't tell you much. Yeah.
Maybe you've already answered this in fact, right? Just double checking. Is it guaranteed that I have a general resolution proof that's polynomial in the size of the input? It's guaranteed. Because if that would be exponential.
Are you guaranteed that CDCL will do it in polytimes?
That's not what I'm asking. General resolution proofs, are they polynomial in the size of the input?
No. They can be exponential, and there are well-known examples, like the pigeonhole, that they're not. Okay, but you're working within that system, and at least what you want to do is you want to get to at least the power of that system, right?
Yeah, the simplest way to understand this is we use our general resolution as a benchmark.
That's right.
But
You're still limited.
the reason for it is
That's right. And the reason why you use general resolution is the other proof systems, it's not easy to search for proofs in them. Here, you can branch on variables, you can have heuristics for branching, and you seem to be able to find these proofs, if they exist, and they're small, fairly efficiently. So it's this trade-off between having short proofs and being able to find them, right? And general resolution seems to be kind of like the sweet spot. So then, besides this forgetting of learned clauses, people do pre-processing, where you eliminate some variables, or you do clause subsumption. You do in-processing, which is you run the SAT solver for a while, you learn some new clauses, and now you do pre-processing in the middle of the run. And all of these techniques turn out to be very useful and important. Now, one other thing I want to tell you before I move to the second part is this notion of assumptions. Yeah? That you may not what?
You may no longer terminate. Because, forgetting last.
Yes, yeah, you lose completeness. Yeah.
You also may not terminate.
Yeah, well, it's the same thing, right? You're searching for a proof, you don't find it. Well, you're not terminating yet. Yes, there are examples where if you forget learned clauses, according to this rule, you'll take exponential time. But most times you don't. So it's this trade-off between what kinds of problems people typically want to solve and these sort of known counterexamples, right? So we're dealing with NP-complete problems, right? So there's always going to be these known counterexamples, known or not, but they're going to exist to any of these techniques, right? Okay, so the last thing I'll tell you about is assumptions, and that is you have a set of assumptions which are a set of literals, and I want the SAT solver to produce a satisfying assignment that makes those literals true. So satisfies all the assumptions, or if it cannot satisfy the assumptions and the formula as well, I want it to produce a clause which is the negation of some of those literals. So in other words, if this clause is saying, I wanted to satisfy all of those literals, no, you can't do that, because at least one of this subset must be false, okay, according to the formula that I have. And that is not hard to do. What you basically do is you force the SAT solver to branch on the assumptions at the top of its tree, and then you do regular search after that. So after you assign all of the literals of the assumptions, you then do regular search. And what's going to happen under here? So you have the assumptions are set to true under here. And under here, you're going to do this regular search. You're either going to find a satisfying assignment that satisfies the assumptions, or you're going to try to backtrack to the assumptions with a conflict. And if you do, that conflict, if you convert that to an all decision clause, you have this clause that I want, which is the contradiction. Okay? All right, so that is the first part. Okay, any questions about that? Now I'm going to talk about the research part, which is this system called MaxHS, which is a hybrid approach for solving Maxsat. And the outline of this part is I'm going to talk a little bit about why you want to have exact optimization problem solvers as compared to approximate ones, and why they have to be general. And then I'm going to talk about Maxsat, which is the optimization version of SAT, and then details about how MaxHS works, and some empirical results. So just like SAT problems, you'll find that in practice, many problems involve some component of optimization. In fact, the Z3 Nicholas Bjorner, he was quoted as saying that that's the thing that most users request most often, is some version of optimization. Because many problems, you need to do some version of optimization. So these are discrete optimization problems, of course, because we're dealing with propositional variables. Right? So you can set these propositional variables true, false, and you have a finite number of them. So you must be doing discrete optimizations. And often these optimizations problems are NP-hard, so they can be challenging. But as we saw with what Kevin was talking about, is about the auctions, the closer you can find, the closer you can get to a precise solution, the more money you're going to save. In some cases, it's worth trying to save as much money as you can. Okay. So there's lots of work, of course, on discrete optimization. And often, though, that work relies on some sort of special structure. Maybe the problem is convex, or it's submodular, or it has bounded tree width, or something like that. And if you have that kind of structure, then you can often do quite sophisticated analysis, and you can get algorithms that work really well. But if you don't have that structure, well, you still have to do something. If you have given this problem, you've got to solve it. You've got to do something with it. Okay? And then, of course, you could have approximation algorithms. But unfortunately, sometimes these approximation algorithms don't work quite as well as you might like. Okay. So this is not new. People in OR have developed mixed integer solvers, Cplex, Gurobi, and they're used quite a lot. And now, recently, we have Maxsat solvers, which offer an alternative that in some cases is more efficient. And now the worst case complexity of this makes some people shy away. But those solvers, Maxsat solvers as well as MIP solvers, have seen tremendous advances over the years. And often it's really worthwhile trying to see if they work on your problem. It may be surprising that they will in fact work on your problem. Okay. So the main attractive feature of such solvers is they don't rely on any structure. So they don't rely on the problem being convex or submodular. So they just throw the problem at them, and if they work, good. And often they do. Okay. So Maxsat then is an optimization version of SAT. And I'm going to discuss a particular way of solving it, which is called MaxHS. So what is Maxsat? Okay. So traditionally, Maxsat has been viewed as the problem where you have a CNF and you want to find a truth assignment that satisfies a maximum number of clauses, which is okay. That's a reasonable version. But a more practical version that's useful in more contexts is to assign a weight to every clause and then look for a solution that satisfies a maximal weight of clauses. Okay? And equivalently, if you think about it this way, you can also think that you want to maximize or you want to minimize the number of falsified clauses. And in fact, minimizing the number of falsified clauses, casting it as a minimization problem, is really how these solvers work. Okay? So your input then is going to be CNF, and you're going to have a cost associated with every clause. And the Maxsat solution then is going to be an assignment of minimum cost, where the cost of an assignment is the sum of the costs of the clauses it falsifies. Okay. So you can also set the cost of some clauses to be infinity. And that means you have to satisfy those clauses. So you can consider some clauses to be hard, they must be satisfied, and some clauses to be soft, they have a finite cost. You can falsify them, but you incur the cost. Okay? So let's take a little simple example. Here we have a number associated with every clause. These are the soft clauses, and that one which has infinite weight is the hard clause. And now you could write down different truth assignments. There's only 3 literals here. And you can see that this one, 0, 0, 0, falsifies that one, so it's cost 4. And it also falsifies this, so it costs 14. And then you go through all of this, and you see that some of these have infinite costs. In other words, they violate this hard clause. And the optimal turns out to be this one, which has cost 3. Okay, so that's the general idea. Any questions about that? Okay. So we know a few things, theoretically, about Maxsat. We know that it's complete for this class fp to the np, which is a set of problems, function problems, that can be solved computable in polynomial time with access to an NP oracle. We also know it's APX complete, which basically means that there's no nice approximation scheme. You don't have an approximation scheme unless p is equal to np. In other words, if you want to guarantee that you're within epsilon of the truth of the optimal solution, you can't really do it in poly time. And but many important problems fall into this class, and Maxsat has been applied to problems in bioinformatics, electronic design automation, operations research, planning problems, etc. And actually, it turns out that the Maxsat encoding is often quite natural, which is a nice thing. So let me give you an example. So this is a correlation clustering example. You have a bunch of objects. You could put them as nodes of a graph. And so you represent them as vertices in a graph. And you have edges between these objects, which say that they're similar or dissimilar. So every edge has a weight. A positive edge indicates these two objects are similar. A negative edge indicates these two objects are dissimilar. And what you want to do is you want to partition these edges, or these nodes, into some number of clusters so as to minimize this objective function. You're going to incur a cost if you put 2 vertices in a different class and they have a positive weight. And you're also going to incur a cost if you put 2 vertices in the same cluster and they have a negative connection. Okay? So you want to minimize the sum, and you don't care how many clusters there are. That's part of the optimization problem. So you have an unknown number of clusters, and what you can do is you can use then log2 encoding of the number of clusters that are possible. You could the most number of clusters you could have is 1 for every node, right? 1 for every vertex, so log2 of n. And then you are going to find this propositional variable, which says that S for 2 objects, O1 and O2, this variable S12 is true if and only if those 2 objects are in the same cluster. Okay? And then you write a bunch of soft clauses. If there's a positive weight between these objects 1 and 2, then you want to satisfy S. You want to make S true, and if you falsify it, you're going to incur the weight. If they're negative weight, then you want to keep them in separate clusters. And so if you do satisfy them, you are going to incur a weight. Okay? And so now if this is a well-known problem, studied quite a lot, and there are lots of approximation algorithms. And this gives an example about why sometimes the approximation algorithms are not as good. The approximation algorithms work much more efficiently. However, if you look at the cost of the clustering, according to that metric, that's produced by these two approximation methods, this one based on round-in a semi-definite program, and this one based on a greedy approximation, you see that the cost is quite large. If you, on the other hand, solve these exactly with Maxsat, you get this kind of cost curve. So there's quite a gap. Now, this, of course, is taking much more time, and it doesn't scale as well, right? But you're getting much better clustering, significant difference in cost of the clustering over the approximation algorithms. So the x-axis is the degree of the completeness of the clustering graph. Okay? So these are fully almost complete graphs, and these are more sparse graphs. So these algorithms work better with sparser graphs, and this is the cost of the clustering over some randomly or some sample of problems. Okay? So even when you aren't able to solve the problem exactly, there's this other technique which is called large neighborhood search. And what large neighborhood search does is it solves a reduction of the problem exactly. So what you do is you take a solution, say produced by one of these algorithms. That gives you a set-in for all the variables. Then you clamp a large number of those variables, and you say, in this neighborhood, can I find an exact solution subject to this clamping? And so if you have an exact algorithm, you can sort of exactly solve this little neighborhood, and then you move that neighborhood around, and that often gives you a much better solution. So exact solvers, even if they can't scale up to the whole problem, using these techniques of large neighborhood search can actually give you good results, even in approximation. And so here are some lists, of different types of problems that have been examined with Maxsat, correlation clustering and MaxClique, fault localization. So there's quite a few different ones, and it's growing. And why is it growing? Why are these applications growing? Because of this kind of behavior. So this is a cactus plot. This is a bunch of instances and how many seconds they took. So every point is the number of instances that were solved within 400 seconds. The number of instances that were solved within 1,000 seconds. Okay? And what's happening here is that, of course, you reach a point where no more instances are being solved. Okay? So you're going up, and you're not solving any more instances in that time period. And so what we see, though, is if we look from 2008 to 2016 and the performance of the Maxsat solvers, we see that before you could maybe solve like 300 instances within 18,000 seconds, and now you can solve much more. So that's on the unweighted problems. Those are problems where all the soft clauses have weight 1. And then you have a similar kind of thing for weighted problems where, again, you get this performance increase. And with this performance increase has come more applications of Maxsat. And this is the solver I'm going to talk about, this one here. OK. So the largest problems that were solved in the 2017 evaluation had more than 6 million variables and more than 13 million clauses. And MaxHS was able to solve that problem in less than 800 seconds. Now, that's a very particular problem, right? It's got a nice structure. You can find a solution. But still, it's showing that the software can scale up to these kinds of problems. And now, Maxsat is quite a bit harder than SAT. And so in that same year, in the SAT competition, they were solving some problems that were as large as 10 million variables and 50 million clauses. So basically an order, well, 3 times as much. Yeah? No, these are not random instances, no. Random instances are very hard to solve. Not much. Yeah.
So you are also including the partial Maxsat into your Maxsat.
Yes, that's right.
So given any problem instance, the complexity of the partial Maxsat is quite similar to the Maxsat.
Yes.
You can just change the weights a little bit.
Yes. Yeah, it's still similar, unless you have a very small number of soft clauses. Okay, so if you have 2 soft clauses, then you have 2 SAT problems. Did I satisfy 1, 2, or 2?
But that's okay, because usually you will have a large number of soft clauses.
Yeah.
At least for the problem.
Yes, you always have at least a few hundred. Okay, so now I'll give you some information about prior methods for solving Maxsat. And those methods basically use a SAT solver and solve it as a sequence of decision problems. I'll go a bit more rapidly over this since we're running out of time a bit. And the basic idea that we're going to need later on is we take this formula, which has soft clauses and hard clauses, and what we do is we add a relaxation variable to every soft clause. So it's a new variable that we add to every soft clause. The hard clauses don't get this relaxation variable. Now, this variable, if you make it true, the soft clause vanishes. It's satisfied. And so therefore, what you can do with these literals is you can use assumption-based SAT solving. You can say, I want all of these to be false, and now the SAT solver is going to have to satisfy those soft clauses, right? That's the basic idea. And so what those SAT solvers do, this particular approach, is they basically encode these linear constraints. I want the sum in the unweighted case. I want the sum of my b variables to be less than k, less than equal to k. In other words, I want to falsify at most k soft clauses. And can I satisfy that? Or in the weighted case, I would have a pseudo-Boolean constraint, and I can convert that into CNF, and I can solve that. Okay, so that's how they work. I will skip over this. It works fairly well, but when it comes to weighted problems, unfortunately, this encoding becomes very large. And so the SAT solvers don't operate quite as well. Okay, so an improvement to that, which is an idea that we're going to use in MaxHS, is to use what are called cores. So a core is a subset of the soft clauses which together with the hard clauses are unsatisfiable. So in this example here, these two clauses cannot be simultaneously satisfied while satisfying that hard clause. So it's a core. So what does that mean? It means that any truth assignment that satisfies the hard clauses, which you must falsify at least one of those. Okay? And so what you can do then is you can extract this core as basically being this clause over the assumptions. So you say, I want the SAT solver to make all of the BI false, right? That's my assumption. So that means I want to satisfy all of my soft clauses. And what's going to happen is if it can't do that, it's going to say, here's a subset of the B variables that one of them must be true. In other words, one of these soft clauses must be falsified. So you can extract these cores using the assumption mechanism. Okay, so I'm going to skip over some of this because I want to get to this, which we're going to talk about today, and where time is going a bit. So the problem with these approaches that use SAT is that they create harder and harder SAT problems. So you try to solve the problem falsifying 10 soft clauses. That doesn't work. Now you try to satisfy the problem falsifying 11 soft clauses, 12 soft clauses. Each of these problems is getting more and more complicated for the SAT solver because it has more range of possibilities with respect to which 12, which 11 do I choose. And therefore, you get this problem. And then with weights, you also have problems. Now, people have tried to encode these clauses in SMT solvers. So instead of trying to encode that to CNF, you could give that to an SMT solver, and then the SMT solver would take care of the, that component of the constraints. But it doesn't seem to work very well. It doesn't seem to help much. I have some ideas why, but you can ask me that offline. Yeah. You need to share the variables, basically, and you don't. Right. So, so as I said, SMT solvers don't seem to offer an advantage here. Now, you can also convert Maxsat to integer programs. So every clause is a linear constraint, but the integer program solvers don't do very well either. I showed you that. Let me go back and show you again. Yeah, so this graph here is Cplex. So that's the integer programming solver. And you can see it's much worse. It solves far fewer problems within 1,800 seconds than the other solvers. So it doesn't do very well. And the basic idea there is that those mixed integer programming solvers really depend on having good linear relaxations. Unfortunately, when you linearly relax a CNF, you can satisfy every clause by assigning 0.5 to every variable. So then you don't get a good approach. Okay, so what we're going to do then is we're going to generalize this idea of cores and take a look at multiple sets of cores. So say that I have the following cores. Clause number 1, 3, and 10, one of them have to be falsified. Clause number 3 and 4, one of them has to be classified. One of these classified. A hidden set of those cores is, of course, a soft clause from every core such that you cover all cores. Okay? Now, it turns out that if I take this as my hidden set, C2 and C5, I cover all the cores, I hit every core, and I have a certain cost. The cost of falsifying C3, the cost of falsifying C5. What we're interested in is minimal cost hidden sets for these cores. And what we do know is that any truth assignment that satisfies the hards, the set of soft clauses it falsifies, forms a hidden set over all the cores. It contains something from every core, just trivially, because every core, you can't satisfy all the soft clauses. Okay? And so that means if I take a look at the cost of this truth assignment, which is the sum of the costs of the soft clauses it falsifies, it must be at least as large as the minimum cost hidden set. So the minimum cost hidden set then is a lower bound on this cost. So if we have a bunch of cores, K, and we compute a minimum cost hidden set, we then get that for every feasible solution, the cost of that must be at least as big as the weight as the cost of this minimum cost hidden set. And so you get this lower bound. And in fact, you can show that if these two meet, then that truth assignment must be optimal. So that leads to this very simple algorithm for solving Maxsat. What you do is you have this theorem, which you can prove. It's very trivial. It says if I take my formula HF and I remove from it a hidden set of the cores, and if the result, that's a bunch of soft clauses I've removed, if the resultant rest of this is satisfiable, and that is a minimum cost hidden set, then that solution is a Maxsat solution. It's optimal. Okay? And there's a simple proof here. So it leads to this algorithm. You start off with an empty set of cores, and of course, a hidden set of an empty set is an empty set. And then you ask the SAT solver to solve all of the hard clauses along with assumptions which say satisfy all the soft clauses, except for the soft clauses in the hidden set. Okay? So in this case, the hidden set is empty. So initially, I'm going to try to satisfy all the soft clauses. Either I'm going to get SAT, in which case there's a solution that satisfies everything, has cost 0, or I'm going to get unsat, and I'm going to get a core in the conflict that we get from assumption-based SAT solving. So I add that to my set of cores, I compute a minimum cost hidden set, and now I remove that minimum cost hidden set from my set of soft clauses I need to satisfy, and I go again. And if I get so that's what this says about this SAT solve. So if I get to this point where actually I find SAT, then I have an optimal solution because its cost is the same as the minimum cost hidden set. If I get unsat, I get a new core, and it must be new because HS hit everything in the old hidden set, every core in the old set of cores, and it doesn't hit the new core. So the new core must be new. And so therefore, I can only do this a finite number of times because there's only a finite number of cores. And so you must terminate, and away you're finished. Okay? Unfortunately, it's a very simple algorithm, but it doesn't work that well. And let's go to that part here. So how do we, so one thing I want to mention though is that how do we solve this minimum cost hidden set problem? That's where we use the MIP solver. Because the MIP solver, it's a hard problem too, but the MIP solver is actually quite effective on solving these minimum cost hidden set problems. And it's related to other approaches, like for example, CARP's implicit hidden set problem, and also there's this idea of logic-based benders. This approach is similar to those. So one of the things that you get as an advantage, even though it doesn't work that well in this base form, is that it's incremental. Every time you call the SAT solver, what you're doing is you're asking the SAT solver to solve the formula with some soft clauses excluded. So the SAT formula never gets too hard. However, the minimum cost hidden set problem gets harder and harder, because every time you go through, you add one more core to the minimum cost hidden set problem. So you get three sources of exponential behavior. The SAT solver could be hard, solving the NP-hard minimum cost hidden set problem could be hard, and the number of iterations you have to do could be exponential. And all three of these are theoretically possible. But it still works fairly well, interestingly enough. So this basic algorithm, if you run it, what happens is that you find out that almost all of the time, Cplex is timing out. So then the problems that can't be solved, Cplex is the culprit. It's doing too much work. So every time you find a core, you solve this minimum cost hidden set, and the amount of time it ends up taking just blows up, right? Dominates. So what you want to do then is you want to improve this basic algorithm by basically minimizing the amount of work that Cplex has to do. And you can do it in a bunch of different ways. You can give better constraints to Cplex. You can generate constraints more cheaply. And then you can try to get away without solving the minimum cost hidden set. Try to solve a non-optimal version of that. So briefly, if you have a core, I could minimize that core. I could remove elements from that core, and there are well-known algorithms for computing minimum cores. For example, this algorithm that we published in 2015. And so you could do that. It turns out that it's rather expensive to compute minimal cores, but you can run this algorithm some number of steps, and you can often take a core that the SAT solver gives you that contains 1,000 or 100 literals in it, and reduce it down to 4 or 5 fairly quickly. And this is very important to do. You can find cheaper constraints by looking at your formula. And the basic idea of this is if we look at a formula, you look at these clauses, you see that they have unit soft clauses. And therefore, although we're introducing a b variable, you don't really need to have that b variable, because the literal L corresponds to whether or not L corresponds to this thing being true or not. And so what you can do is you can look at your unit soft clauses, and you can say, do I have any other clauses that contain only unit soft literals? And now I can take those and add them directly to the Cplex solver. Because remember, the Cplex solver, which is getting these cores, is having variables that indicate the truth or falsity of the soft clauses, and that's exactly what these literals are. So in many problems, I can seed the SAT solver, the Cplex with all of these problems. And what you get then is you take the original algorithm, it runs like this. And if you add minimization, you get quite a good increase in speed, in number of problems solved. And then if you add these other techniques, including the seeding, you get up to here. So that works well. Now, perhaps the most important innovation, though, is this idea of, do you want to compute this all the time? This is only useful if you go that way. So suppose we just got rid of that. We would save a lot of time, right? So we no longer compute a minimum cost hidden set. Instead, we just compute any hidden set. All right? So now we can use any hidden set. We go to here. Well, if we take that branch, if it's still unsat, that's still a valid core. We're good. But if we take this branch, now what we've done is we've removed from the set of soft clauses that the SAT solver has to satisfy more than we had to. And therefore, this is no longer necessarily optimal. However, it could be that it's still cheaper than any model we've found so far. so we can keep track of the incumbent, as the MIPS people would say, which is the cheapest model sound so far. And if it's cheaper, we install it as a new incumbent. Then we must continue. And how do we continue? Well, we continue by finding another hidden set. Now, we just have to be careful that it doesn't cycle, that we don't continually return the same hidden set and find the same core, right? But you can do that in different ways. So we find another hidden set, we go down and we go through this loop, and we keep on doing it. And the way that we make sure that this works is you can use this condition always eventually. That's all you need. This is the most general condition. Basically, what it means is that occasionally you must compute the exact minimum cost hidden set. You can't get around that. You have to do it occasionally. And so occasionally at some point in accordance to some policy, you compute this minimum cost hidden set. And now you know that this forms a lower bound. And so you get a new lower bound. And therefore, you can check to see if the lower bound equals the upper bound. In other words, the upper bound is the cost of your incumbent. The lower bound is the cost of your minimum cost hidden set. And there's two places where you can find a new incumbent that's cheap, or you could find a new lower bound from this minimum cost hidden set computation. And when the two match, you stop. You have an optimal solution. And if you do that, then you get from this one here, which is the graph I showed before, you get quite a bit more. And then over the years, we've seen more further improvements in different things we've done. And we've, on the same benchmark suite, not the same as this one. This is a different benchmark set. But we have a steadily improvement of problems, about 10% over those 2 years. And recently, we've done a few other things. One of them is that we use Cplex as one of the non-optimal solvers. So there's this technique in Cplex where you can use callbacks. You can say stop when you find a feasible solution, even though it's not optimal. And then that feasible solution is a non-optimal hidden set. I can use that. And that's very effective because it's actually better than the greedy solutions you can find. And then you are dealing with an LP. Cplex has an LP, which is the linear relaxation of the hidden set problem. And from that, you can use this idea of reduced cost fixing. And what's reduced cost fixing intuitively? When you solve an LP with simplex, you get to an optimal solution. You get a basis as well, and you get a number associated with the variable that says if you move that variable off the solution that's in the optimal, you would incur at least this much cost. If you move it by 1 unit from 0 to 1 or 1 to 0. And so what you can do is you can use Cplex to get this derivative cost. And if the derivative cost says, okay, so say that, for example, you've set a variable to be 0 in Cplex. It says you must satisfy this soft clause. You can ask it, well, what happens if you falsify it? What would the cost increase be? If that becomes bigger than your incumbent cost, you can fix it to 0. And you can do the same way, the other way around. If it says, I must falsify this, what happens if you satisfy it? Then you get another cost. And if you look at what happens here, you see that there's quite a lot of soft clause fixing that occurs. So many of these instances don't have any soft clause fixing. But on 1266, you get some number. In some of the cases, you get like 1 million soft clauses being fixed by this technique. And lots of instances, you get more than 500. And then if you look at the log 2 ratio of the performance, which basically is this log 2 speed up, you see that there are many instances, 15 instances, where you get more than a 4 factor of 4 speed up, although sometimes there are about 8 instances where you get more than a factor of 4 slowdown. But generally speaking, you get more speed up than slowdown. So it's quite effective. And then the other thing that I'll mention is that we had this interesting paper at JAIR 2018, where we asked the question, okay, suppose you have a SMT formula, not just a SAT formula. So you have 3 things that are going on. You want to do optimization. You want to do propositional reasoning. and you want to do theory reasoning. And so what we did is we presented this sort of abstract reasoning calculus, the set of rules that you can apply in an arbitrary sequence, which will invoke either the SAT solver or either the SAT solver or the simplex solver or the SMT solver to do whatever particular type of reasoning, and it eventually converges to an answer to a problem of maximum SMT, or max SMT. And then there's a little bit more data. In the 2017 evaluation, MaxHS did well. It came second place in the unweighted case, but on the weighted case, it performed much better. So these are two instances of MaxHS performing much better. And basically what's happening here is that in the weighted case, the SAT-based Maxsat solvers have to translate basically to pseudo-Boolean constraints, or they have to deal with the weights in some other way, a method called clause cloning, which also increases the size of the formula. And so when you have formula problems with large number of weights, they don't do very well. Unfortunately, in 2018, MaxHS got beat by another solver, which indicated to me that these other methods also had some very interesting techniques. And so right now we're trying to figure out how some of those techniques can be imported into MaxHS. That was on the instances that were used in the evaluation. Later on, I checked on a wider set and verified that, yeah, MaxHS still is better. This approach, this hybrid approach, is still better when you have more than two weights in your self clauses. And so, pardon? RC2 is a SAT-based that uses cores. I can tell you more about how it works. And the last thing I'll mention is that it's open source. You can get it by this website, maxhs.org, download it. Cplex is not open source, but Cplex, if you can get an academic license for that and use it. It plugs in, and so you can get that. It has the latest version there. And you're welcome to try it and let me know what you think. There are different things you can do with this idea, which I think would be interesting to pursue. One is that right now what we're doing is we're solving Maxsat. So you have a formula that is a CNF. You could just as well have a formula that's a mixture of a bunch of linear equations and a bunch of clauses. And now you could have both of these solvers working, and as long as they converge to an agreed upon solution, then you can solve that problem. And this is an architecture that I think could have, some interesting applications. So we're working on getting that going. And that's it, I think. Thanks.